So let's start with the presentation. And first, there is a question. So what's the difference between these two devices? So visually, in fact, there is no difference. But one is sterile and one is not. Or at least that's what I'm telling you. So yeah, it's true that there is no difference visually. But indeed, what does it really mean, sterile? What is the real... what is the explanation? What is really the meaning of sterilization? And I just would like to start with a small story that happened 1 month ago, or something like that. When I visited the facility I'm working at, mainly in Petit Rechin, so that's located 1 hour drive from here. And I went through the warehouse with a guy. It was a consultant for a lean manufacturing project. And we went through the warehouse, and yeah, I was explaining him a bit, but suddenly he said to me, but hey, wait a minute, what are you doing here? Because we are just going through the warehouse, and in the incoming warehouse, it's exactly the same as what is in the the goods ready for shipping. So what are you doing here? So I really tried to explain him what we were doing in that facility. So that's an ethylene oxide sterilization facility. And I will try to do the same with you this afternoon. So to really explain you the basics of sterilization and of sterility. But in fact, sterilization is a battle against invisible enemies. It's a battle against microbes. And yeah, of course, you do not see them. But based on the definition of the standard, a sterile product is basically when you won the battle, so when you were able to kill the microbes. So that's really the definition, so quite very simple. So what is a sterile product? That's a product free of viable microorganisms. Quite easy to say. But when you are thinking a bit further about that, that's not easy at all to obtain. Because how can you demonstrate the absence of something? That's not something really easy to do. Even if you test all your products, all your batches, first, you will not have products anymore. That's first thing. But secondly, how can you make sure that you can recover them, that you can detect all of them? So that's a second thing to consider. So that's the reason why sterility is only described as a probability. So that's really a key word to remember when you are thinking about sterilization. That's probability, only probability. There is always a chance or a bad chance that you have some unsterile products. And it's even described that way in the regulation. And a sterile product is in fact a product for which you can claim that you have less than 1 chance in a population of 1 million of having an unsterile product. So that's really the definition when you are seeing sterile on the label. That's the meaning of that. But yeah, let's go a bit deeper together and see what is behind that, and also see how we can what are the different possibilities to get that sterile product. And how will you select that method? Because there are various different methods. Today we will only talk about a few of them. But definitely you have first to think about the nature of your product. So maybe it will, it's not able to resist to high temperature. Depending also on the intended use of your product, your choice will be different. Heat sterilization is definitely one of the more popular one, and you probably all experienced that at home. Just by doing some fruit jams or boiling your baby bottles. These are a kind of heat sterilization, I would say. On an industrial scale, for the medical devices, the two main popular technologies are ethylene oxide and radiation. So radiation, we are talking about gamma ray, about E-beam, so accelerated electrons, and X-rays. So we will talk about these two a bit further, and there are other technologies like moist heat, dry heat, also VHP, and also I will talk briefly about an oxidizer, which is another option. Just to give you an idea about the market, about 50% of the medical devices, of the sterile medical devices, are sterilized using ethylene oxide. The rest is using gamma sterilization, and the remaining part is E-beam and also other methods. So you really see that gamma and ethylene oxide are two big players there. Maybe also something to clarify before going further, that's to make the distinguish between decontamination versus sterilization. And I know after that you will have more word about cleaning, so that's I will not go deep into the definition, but cleaning, that's really removal of contamination. Basically, that's what it means. If we go a bit further, we are talking about disinfection. So there we are starting to talk about bioburden. So really to remove a surface bioburden till achieving a safe level. So this is definition from GMP Annex 1. Then we go to decontamination. So what does this mean, decontamination? That's a process that eliminates the viable microorganism, viable bioburden via a process, via a chemical agent. So then you will tell me, but what is the difference between decontamination and sterilization, which is here the last step? And really the difference between these two, and that's something important to keep in mind, is the validation. When you are talking about sterility, about sterilization, you are talking about process that is able to provide a predefined sterility assurance level. So that's the main difference between decontamination and sterilization. So you can do sterilization, you can do decontamination in our facility, for example, in Petit Rochin, but not all the process can claim for sterility if they are not fully validated. And also something important, that sterility is not only about the sterilization process itself. It's much more than this. And the first thing to consider is the initial contamination level of your material. So all your components have to be have to be controlled about their initial contamination level. About the cleaning, what kind of disinfection and cleaning procedures do you have in place, the type of environmental control you have, personal hygienes, all these kind of things are really contributing to the initial level of contamination of your product, and then of course to the final sterility level of your product. So initial contamination level, but also the equipment is key. So keep control of it, the maintenance of it, the calibration of all the sensors are really important. And lastly, the product preservation. So before, I mean about the packaging and the sterile barrier, but also about the storage. So after the sterilization process, how do you make sure that you keep that sterility status? How do you select your sterilization method? Three things to consider. First one, and that's really the first element to take into account, that's really product constraints. So talking with you to identify the constraints of your product, of your specific product. So, for example, can you accommodate high temperature? Till which level? Can the product resist to humidity? Yes or no? Can the product be exposed to radiation? Yes or no? What kind of effect do you have if you expose them in a certain doses, etc.? So these are the really important things to identify when you start a sterilization project. Then, of course, but that's linked to the first one, you will choose for a sterilization methodology. So as said, it will probably be radiation or ethylene oxide. But the first questions you will ask yourself will surely help to go for one or the others. And if it's difficult for you to say which one is the best, then you can do a kind of screening. So just to make some pre-test to see which one is the most recommended for your product. And then to have a cycle design which is appropriate, because there also in the different technologies, you can have various possibilities that could accommodate the product constraints. So for example, in ethylene oxide sterilization, you can have cycles with 50 degrees Celsius, which is great. But if your product cannot resist above 40 degrees, we can develop cycles at 40 degrees and play on other parameters. The same for radiation. 25 kilogray is the most common dose, but we can also develop a sterilization method with a lower dose. So that's really the three factors to consider to, at the end, get a sterile product. And about the selection of the methods, the earliest is the better, is the best. So really, most of the time we see customers coming to see us when they are already in the clinical trials. I would say that's good, but that's probably too late. It's always better when they start contacting us, or at least thinking about sterilization very, very early during the product development phase, because at that time you have all the flexibility. You can adapt some of your components, maybe just thinking that it will be exposed to gamma radiation, then you can change and adapt a little bit to make sure that it can go for that methodology. So that's really important, and will make the way smoother, I would say, for the rest of the project. Also for packaging, that's important because there are some constraints really linked to the method you will select. Some basics about sterilization, and again, that this is high level picture, but I think it gives a good idea about the sterility assurance level. And something to really consider is that there is a linear relationship between the initial bioburden, so the initial contamination level of your product, and the treatment applied. Can be the dose or the exposure time. So that's really a linear relationship. So it means that you can predict really what type of dose or what time of exposure you need to apply to a certain product to achieve the sterility assurance level. And really that's the main principle of any validation for terminal sterilization there. So that's really starting from your, here we have the curve for biological indicators, so we can call it the challenge. And most of the time your product will be below that, so you will start, for the challenge you usually start with a population of 10 exposure 6, so 1 million of spores, and you do all your validation against that. So it means that considering that challenge, you will apply it, in that case 25, let's say 25 kilogray, to achieve the sterility assurance level of 10 to the minus 6. But you see that it's over the bioburden level, which is giving an additional safety margin, if you want. So we always have that two kinds of levels. The validation is made on the challenge, but usually your product is made of lower contamination, even if it's now possible also to really make the validation based on the bioburden itself. So it's a method that is coming more and more popular, I would say, because you can customize your cycles and have something more adjusted, I would say. But the main principle is always with using a challenge. So it means that, again, that's another way to present things, but you would like to have that pyramid of resistance with the bioburden at a lower level compared to your microbiological challenge. The associated laboratory tests to that phase are really for the product bioburden. We do bioburden tests, of course, before sterilization, and we do some product sterility tests after the sterilization. For the BI, we call it the challenge or BI sterility tests. So these are the tests done by our colleagues at Nelson, but definitely that's to show, that's to demonstrate that pyramid of resistance. And it's the same principle, whatever sterilization method you will select. About sterilization by irradiation, two ways to get product irradiated. First one is gamma sterilization, and second one is electron beam accelerator or particle accelerator, and then you have E-beam or X-ray. So just briefly go through these two technologies. And again, to illustrate and give you an idea about what type of radiation we are talking about. So 0.1, that's the level when you are going to the hospital for X-ray chest X-ray. And here is the level we are talking about for sterilization. So really much higher compared to the lower scale there. The idea here is to really damage the DNA of the cells. So the photon will make ionization to the DNA and really make the cell unable to replicate. So it will die at the end. The source of radiation is mainly cobalt. So that's cobalt 60. And the way it's presented here, it's so you have the source here, so really the source of cobalt, and in blue you have the conveyor. So really the product is going there and circulating around the source. You see that the cobalt is having an isotropic radiation around that, so it's really like, that's an image, but it's like a roasting chicken. So really, that's the image you can keep in mind. But really, you have your chicken less or more roasted, depending on the number of tour it's doing around the source and how many times you let him in the irradiator. So really, very basically, that's the principle for gamma radiation. For an E-beam, really different. It's generated by electron accelerator particles. So it's there. And here the beam is generated here. And you have the conveyor of the products. So products are just going through the beam and are exposed, so it's a very thin ray, really, and the product is really going through. So you see that the principle is different compared to radiation, so more precise, but also you cannot sterilize a whole pallet at once, for example. So here it's a sterilization by box. And here also to illustrate the difference between gamma and E-beam. rays. So you see that gamma is really going deep because there is no mass really, that's photon, so it can go really far into the material. Where for the electron beam, that's not so deep. But anyway, there are things to balance these two technologies. But this is really the difference between the two. About the methodology for the validation, so the most popular one is the VD max method. So there you have again the same pyramid of resistance, where here that's a scale that has been established, that it's available in the standard. So they've selected a challenge, which is a very highly resistant strain. And they compare it at different different radiation dose. And based on that, you can establish the level of dose you need for a certain level of bioburden. So VD max at 25 kilogray is suitable for devices with a maximum level of bioburden of 1,000, so which is already quite comfortable. So that's why a lot of devices are sterilized using that method. But again, the principle is the same. It's monitored using dosimeters that are distributed in the pallets to identify the minimum and the maximum dose. So you make sure that you at least achieve your 25 kilograys at the most difficult place in the pallet. So minimum and maximum dose are also important to preserve the product. In gamma radiation, you need to do some quarterly dose audit. So you need to repeat your validation, I can say like this, or to verify it on a 3-monthly basis, and it's based on bioburden. So you do a bioburden test, you do a verification dose, which is lower compared to your routine dose. You do some sterility test, and then you confirm that you are still having the right sterility assurance level. About sterilization by ethylene oxide. Ethylene oxide is really an extremely reactive gas, and again it will create reactions with the DNA of the cells, so of the proteins of the cells, so it will not be able to replicate anymore. That's the last choice, so that's definitely not the technology you would like to select at first, but sometimes that's the only one. So there is still space for that for the technology for sure. Here that's a picture of a sterilization chamber. And also maybe something you do not realize, but there the products are sterilized in their final packaging. So really the pallets are entered into the chamber the way they are coming in the truck. And we have different capacities, so from 1 pallet to 32 pallets chamber, which corresponds to a full truck. And that's quite flexible technology because you can group products together as a family or as a product category, so that's quite good for if you have very custom packs, for example. That can be a convenient method. The packaging needs to be adapted to ethylene oxide sterilization. You need to have a packaging that is able to let the gas to penetrate, resist to vacuum. Of course, protein-based material are not possible. Liquid material not possible either. And for batteries or powder, that needs to be assessed first. For parameters to consider, I will not enter into the details, but humidity, exposure dwell time, temperature, and EO concentration are the main ones to consider. And it makes it quite complicated, but also flexible, because it means that when you have a high concentration, you can play with a lower lower exposure time, and the opposite is true also. 3 phases: preconditioning, cycle, and aeration. And in parallel, we are using some challenges. So for the biological indicators that are incubated for 7 days. here is an example of biological indicator. And here what we do also in sterilization by ethylene oxide is having internal challenges and external challenges. So it means that in a routine, we just use the external challenges. So we do not have to open the boxes and take out the challenges from the internal boxes, which is more convenient. But the principle again is the same. Having your challenges more resistant compared to your bioburden. In ethylene oxide, you need to care about the residuals. So there are three types of residuals: ethylene oxide, ethylene chlorohydrin, and ethylene glycol. And also you need to consider, so the limits are different depending on the type of end use of your product. So it can be limited exposure, prolonged, or permanent contact, like the implants, for example. You will have different categories there, different limits. And recently we had a new standard published about the neonates. So there again you have different limits to apply if your product is to be used on small patients like babies or even newborns of 1 kilo. It's not the same compared to an adult of, let's say, 60 or 70 kilos. Some examples of products that are sterilized by ethylene oxide here. So surgery, catheters, but also some APIs, pre-filled syringes, implants, auto-injectors, and so on. Here I have a table, let me see, whoops, with a comparison between the three technologies, so gamma, E-beam, and ETO. I will not go through that in the details, but at least you have it for reference in the presentation. So really, I think that's good to have a first screening or a first idea about the ideal technology for your specific product. Just a few words about an alternate possibility, which is quite new in our company. That's about an oxidizer. So an oxidizer is the sterilization with nitrogen dioxide. It's really a surface sterilization technology, so it does not go so deep as would do the ethylene oxide, but anyway, it can be good for some specific applications. It's a short process, and quite easier to use compared to ethylene oxide because it's not flammable, non-explosive, so that's more easy to manipulate, I would say. It's quite compatible with a lot of material, but not with a cellulosic-based material. So there you need to be careful. And we go back to the packaging definition we talked about before. It's good for temperature-sensitive product because the process is running, let's say, between 10 degrees and 30 degrees. The residuals are lower. For now, that's small volume possibilities. Maybe scale-up will come, but for now, it's still ongoing. But maybe that's something you could consider for the sterilization of your medical devices. So just to conclude, different ways to get there. So many options. You can go with ethylene oxide sterilization, with radiation sterilization or whatever. But visually, at the end, your product will still look the same. This is visually the same product, but hopefully now you realize that it's not totally true, because this product is sterile, so it means that it's safe. It's safe to be used by patients, to treat diseases and to help to preserve healthcare. So that's really the difference. And really, sterilization is a battle against invisible enemies. So I just concluded that way. So sterilization, the invisible crucial process. So, and of course, we are there, or I am there to answer your questions if you have any. And definitely to have a good partner for sterilization is key. And I think Dr. Jenk explained this morning about CRO selection, but I think to select the right partner for sterilization is also key. So please challenge us. That would be with pleasure that I would answer your any questions. So thank you.